Hey everyone, how's it going? We got an exciting round today. It is the first round of Google Code Jam 2022. And here we go. So, looks like we have 5 problems. And let's check it out. Okay. Dashes above and below. Right, and plus signs each corner. Okay, let's see. Oh, you just print this, that's it. Okay, this should be pretty easy. So let's see, so we're given R and C. Can they be 1? They have to be at least 2. Okay, so yeah, there's basically just there's the even string, which is going to be plus minus, and then it's going to end in plus. And then there's going to be the odd string, which is actually very similar, so we can do this. It's going to be like that. And then we're going to do and if I is 0, then if I is 1, we're going to replace the first one. Oh, I guess we can just do that with either. Cool, and then we just need to oh, that's downloading, that's not what I want. That looks pretty good. Alright. Maybe I do want downloading actually. I can just submit this, let's do it. Right. And while we're waiting, let's do the next one. There's T's. Oh, 3D's good. Okay. $500,000 of 150,000 and 50,000. Wait, what? Oh, okay. I get it. Okay, so we're just taking the min for each color across the 3, and I mean, we kind of have a 3x4 array. I'll do a vector. Make an infinity constant. I actually technically didn't need to read all of that. I could have just used this single vector. I'm gonna put this if min inc, if the sum of it actually is less than 1e6. 26. So less than 1e6, then we're going to do impossible. Otherwise, maybe this is better. Just return extra is going to be okay, and then what we're going to do is use this function output vector. Yeah, I'm just going to output vector and that should do the trick. So I think that's fine. That looks good. And so we did get this first one. Okay, Gendy's got 3 problems already. So let's keep going. D1 million, all right. Okay, so you should always start from 1 because that's the only thing that makes sense, yeah. Got this one, yeah. This is, I think we could just do this with a heap pretty easily. So that's actually heap. Just build it. This is by default a min heap, sorry, max heap. So we actually need to convert it to a min heap. And essentially while the answer, no, heap.empty, if heap.top is less than the answer, that's no good, so we need pop. It's gonna be at least answer plus. And that's pretty much it. Let's try this. Let's see. Oh, what am I doing? Okay. Yep. Language here and submit. Keep moving. Is this a tree? This is a forest? Okay. Yep, got it. Cool, sitting in 6th. Okay, yeah, you just go up. You just go up the tree. Up almost. Okay. Oh, if they're not pointing. Okay, so just 4, 6, 60. Maybe he does this. Okay. $100,000. Yep. No solves for either of these. All right, so we've got a tree, we've got a forest, but we can just think about a tree. Got the leaves, and you need to pick an order for the leaves to maximize this. So there's probably a greedy approach that would work. So if we want to maximize it, let's see. The only thing that matters is where something branches. So when you have something that branches, then you max of these is 50, and then if this is like 20, 30, 60, 20, 60, 30, then this is 60. You want to do the 50 first and then the 60. So yeah, so we look at all of our children, we take all of their values, add up everything except the smallest one. The smallest one we bring up. And then we want the parent. So the parent is going to be, okay. We need to track children. Okay, so for each child, we're gonna take the results. And or we can do like well, so the size is getting 1. If sorted outside, if sorted out empty, should be equal to 1. Sorted 0 equals max. Sorted 0 f of our node. And pass that up. No, it's essentially this. What happened now? Oh. Okay, looks good. Submit it. Andrew and Kevin doing well. Alright, and one more problem. Good, nice, got it. Well, that's hidden, okay. Alright, sitting in third. Let's keep going. N rooms. Okay. Oh, okay. It's an interactive one? I see. Identify what room you're in and see how many paths. What are you told? Why would I use the second one and not the first one? How big is K? 8,000. Okay. If most have 1, but then 1 has n. I see. Yeah, if you have a star, most of them have 1, and one of them has n. If you just pick a bunch of random ones, you're not going to get within 2. But you're not going to get within a third. Okay. So you need to walk around in order to hit the ones that are more likely to have a lot of passages. So there's only one visible phrase. Okay. So you either get it or you don't. Yeah, give a star. Okay, so then it doesn't have to be a connected graph, does it? Okay, and this one helps you find the rooms with a lot of passages. Okay, so we could do something like taking 2 sets of rooms. We could do a bunch of the first operation and the second operation. The ones that we get from the second operation are going to be in a separate bucket. They're going to be the high count rooms. So what's 25 divided? 12. So if anything has a lot, I should have a very high chance that we would find it. If anything has really a lot, we should find it. Yeah, but I see. how much should I think and how much should I just go for it? Alright, I'm just gonna think a little more, try to come up with a reasonable idea and then go for it. So if something has, how many can there be? There can be, oh, there can really be a lot, right? Yeah, how do you define the probability distribution of picking a certain node? Going when you take out a neighbor? It's something like, there's whatever the degree. So kind of model is picking with the likelihood that's proportional to the degree, but even then, I don't know if that's accurate. Yeah, what do you do with that? A lot of failed submits, one failed submit. This seems like quite a tricky problem. I think that's reasonable. All right, let's just do it. That's the if and this case. Hold 2 to do that? Maybe you don't need to do that. I think we should just go ahead. Room and passages. Okay, so we're going to do a T and we're going to do a W. Oh, Andrew tried it. Great. I don't know if I need to do this, but I will. I can randomize the rotation. Oh no, I can just do this. No, I don't need to do that at all. I want to find a missing. Okay. That's what's missing. There's also vectorable found, neighbor found. So first we find a missing. Just in case. Right, it's accessing. All right, and then we're gonna walk. Okay, so else non-found plus plus, and if does it have to be an integer? Integer. Okay, so sum 0. Count is 0, we just go with 0. Otherwise, we go for. Let's do this. So I didn't use this. Okay, so teleport to 3. We're at 3, which is 1. Walk goes to 1, which is 3. Oh, I forgot to divide by 2, didn't I? Yeah, and it was interactive. Okay, Python 3 interactive runner. 3 local testing. Why is this stop high 3? Is that why it's getting confused? Oh, it's edebug. This is too slow. Okay, I think we're good to submit. Let's do it. I wouldn't beat Andrew either at this mission. It's doing pretty well though. Nice. Alright, that is confirmed 4th place. Good stuff to all the top 3. I'm not sure who PWI Peanut is, but good stuff to Kevin and Andrew. Let's see. I'll go ahead and let's pull these problems, and we can talk about. I'll talk about how I approach each of these ones. So, I got 100 correct. I wonder how many I got on the real test. Anyway, pull this up. Cool. So first problem, pretty simple one. It is the qualification round after all. Basically, you just get an R and a C, and you need to print this sort of card, which is basically just the pattern that you see here, but the top left corner is punched out, so you just need to modify those to be a couple periods here. And the key idea I had was just build this string, the pluses and minuses, and then build this string, the pipes and periods, and use those as our key building block to output this. You just need to alternate them. And then there's a special case for the first 2 rows. For the first 2 rows, we need to replace the first 2 characters with periods. And so that's how my code works. We're just building up these strings here. And then again, special case for row 0 and row 1. We replace the first 2 with the 2 periods. All right. Now let's look at problem 3D printing. So for this one, we have, we need to make basically 10 to the 6, 1 million units of ink, and make sure all 3 of our printers can handle that. They need to print the same color distribution. And we have 4 colors in each printer. So basically the idea here is that, when you have these sets of 3 printers, so this is your first printer, this is your second printer, and so on. The maximum you can get out of each color is the minimum printer for that color. So for example, for this 4th color right here, we have 500,000, 300,000, 200,000. The max we can get for that color is 200,000 because we can't go more than the min printer. And so that's kind of our baseline. So we actually just compute that. We compute the min ink across the printers for each of the 4 colors. And we need to hit at least 1 million. So one obvious thing we can do is if the amount that we have in total is less than 1 million, then we're immediately at impossible. We can't hit 1 million. And then the only thing left we need to fix is we need to make the sum exactly 1 million. So we need to remove any extra ink in order to get down. And this is the code to do that. It basically, we keep track of how much extra we have, and then we try to remove an amount from each color, which is the minimum of the still remaining amount of extra, and the amount of ink for that one. Because we don't want to go negative on the ink, and we don't want to remove more than the amount extra we have. And one tricky thing here is we do need to do it for all 4, because for example, if actually, I guess based on the constraints, the first 3 would be enough. But you know, the point is, if you have 0, 0, and you have, you know, 1 million, 1 million, it's not good enough to only remove the extra from the first one, right? Because in that case, you're still ending up with 2 million. So that's why I loop through all of them. All right, that was 3D printing. Those two are definitely the 2 easiest problems out of the set. Here in this problem, we have a number of different dice. This is a D1 million. So we have a number of different dice, and each one has, we know the number of sides for each one, and we want to form a straight. So a straight can be something like 7, 8, 9, 10, and we want to make the longest one possible. The key observation here is we should start our straight from 1. Because let's say we start our straight from something not 1. Let's say we do a straight of 3, 4, 5, 6, 7, right? If we have 3, 4, 5, 6, 7, then because of the way the dice work, we can replace this with 1, 2, 3, 4, 5. Because the die that has a 3 will definitely have a 1. The die that has a 4 will definitely have a 2, and so on. I'll make this a little bigger. In particular, any die with the number x also has all the numbers smaller than x. So for that reason, if we can make any straight starting from a number bigger than 1, we can make the same straight starting from 1. So we might as well start from 1, because that is going to be our optimal answer. And then the question is just how do we figure out how to make the biggest straight starting from 1? Well, this is just a pretty simple greedy algorithm. So first we need to find a 1, then we need to find a 2, then 3, and so on. And the greedy idea is each time we're looking for a die for our next number, we're going to pick the smallest die possible. So if we're just trying to fill out, you know, a 7, and we have one die with 8 faces, one die with 9 faces, one die with 10 faces, we should always use the one with 8 faces, because there's no benefit to using a bigger die there. In fact, you should save your bigger dice for future numbers. And so we always use the smallest number that is at least as big as the number we're looking for. So the way I implemented this is I did it with a heap. I used a min heap on the dice sides. And so essentially, I keep track of my answers. So I'm starting at 0, and I'm trying to get to 1, then to 2, then to 3, and so on. And I just remove all the numbers that are too small. So remember, I'm looking for answer plus 1. So if it's less than answer plus 1, or if it's less than or equal to answer, then it's too small and we can remove them. If we've run out of numbers, then we break and that's it. Otherwise, we pop the smallest number and we can go one further. So that's the implementation here. This is n log n, so pretty efficient. And yeah, that's the main idea. There are other different greedy ideas, I'm sure, but this is just the one that came to mind for me first. All right, chain reactions. So this one is a tree problem. It can feel a bit tricky at first, but there's a pretty simple idea underlining it. So the idea is essentially, if we're going to have a node that branches out into multiple children, we need to decide essentially the order that we're going to pick the leaves from its children. And the main idea there is, for example, you can see in this example that they've given us that we could start with the 50 or we could start with the 40. And whichever one we start with will actually get the 60. And the other one later will get its own number. And so for that reason, we want to start with the 40. And essentially kind of try to replace the 40, which is a smaller number, with something bigger above. We gain the most benefit from replacing the smallest number with something bigger. And so this if you continue in this thinking, this gives you a greedy algorithm where essentially whenever we branch out, the smallest result below is what we're going to want to bring upward and get our best chance to increase it, right? So in other words, you can see from this example, we would rather increase 40 to 60 than increase 50 to 60 because there's more benefit there. And this idea applies recursively. So the idea is that when you're a node in the tree and you have a branch of multiple children below you, you can sort all the children below you by their current max, which is the max up to getting to your current node. So in this case, this one would be 50 and this one would be 40. And all of the ones that are not the minimum, you will just add them up right now, because you're going to take the minimum, bring it up, and then all the remaining ones will end once they hit your current node. So all the ones that are not the minimum, you just add them up right now, and then you bring the minimum up. So there's always one number you're bringing up. And in this way, the implementation is actually pretty simple. It doesn't even look like a tree implementation. The reason is because the fact that they told us that the parent of each node is a number less than the node, that actually gives us the opportunity to just iterate through in a simple loop and kind of simulate DFS in that way, because we know the order that things are going to get visited. Yeah, so basically the idea is here, we take the children, we take the number that they're bringing up, and we sort those. We take everything that's not the minimum, so I keep taking the maximum until we get down to an array of size 1. And add those all up to the total. We were left with one number remaining, or sometimes 0 numbers. We should make sure we have at least one number. And then the number we're bringing up from this node is the max of the minimum of the list and the current value at the node. And just iterate all of those, bring them up. And then one thing to account for at the end is we didn't add up the root of the tree because it never had a branch. We added up everything that branched. So there's one thing remaining at the top. You need to add that up. And then because this is a forest and not a tree, we need to iterate through and find all of the roots, which are nodes that have a non-existent parent. In this case, I made it a parent of -1. And in that case, just add up their up value. And yeah, so that's it. This is n log n. You can actually make this O of n time, but I didn't bother doing that because it's not necessary here. The point is just that you don't actually need to do a full sort. You can just find the minimum and you're good. All right, and in the meantime, we can check the scoreboard. So, oh, that's funny. No one else has gotten 100 points in the last about 12 minutes. So yeah, Kevin and Andrew and I were all super close in timing, so kind of funny there. I guess this score is still TBD because it's not judged yet. But I imagine if you pass the first two, you probably pass the last one. I guess there's potential for things like if you didn't realize your solution is slow or something along those lines, but I imagine most people who at least think that they should pass this one would. All right, anyway, one more problem to talk about. So this one is Twisty Little Passages. It's a graph problem and it's an interactive problem. And so we've got a cave, it's just a graph basically. We've got n rooms, so n nodes, and there are edges that connect these pairs of nodes bidirectionally. And it's a simple graph, no self loops, no multiple edges. And nothing is an isolated node, so every node has at least one edge. We can do k operations, and each time we do that, we'll end up in some node, and we'll be told what room we're in, and how many passages are connected to that room. And so we can do k operations. Choices of operations are pick any room and teleport there, or we can walk through a random passage from our current room, and it will take us to randomly to one of its neighbors. And you can't choose its uniform. Yeah, and so we have k operations, and we need to estimate the number of total passages in the cave. And we need to be within essentially 1/3 of the actual answer. In order to pass a test case, and we need to pass 90% of test cases in order to pass. And so the constraints here are really important. N is up to 10 to the 5th, between 2 and 10 to the 5th, and K is always 8,000. So we can't just, the first thought is like, oh, if K is really big, then we could just teleport to every single room and then get the actual number for that room and add that all up. But K is not big enough to do that. My first thought here was actually that, why don't we just use operation 1, K times, and once we do that, we're going to get a random sample of all the rooms, and we're going to know how many passages each of the rooms in this random sample had, and we can use that to estimate the overall number of passages. So this makes sense, and it's, I think, from a statistical perspective, it's a good estimator. The problem is there can be a small number of nodes that have the majority of the passages, and it's likely that you won't catch them. So for example, you can have a graph where there are two kind of center nodes and then a bunch of other nodes. The center nodes connect to everything, and each of the other nodes only connects to the two center nodes. And so you have roughly 2n edges in that case. But if you just pick 8,000 random nodes out of 100,000, most likely you never hit one of those two special nodes. And every node you saw would have 2 passages. And so you would assume, okay, in that case, there's 2 times n divided by 2, because each edge gets counted twice. So we need to divide by 2. We would estimate n passages, and we're off by a lot in that case. So essentially what I did to fix, this isn't like super rigorous. I didn't take the effort to do like a statistical proof of this or anything, but my thinking is, okay, we're more likely to find those many passage nodes or rooms if we take a random neighbor of a random node. So in particular, if you think about that case with those 2 special nodes, if we pick a random node and we pick a random neighbor, we are highly likely to hit one of those 2 nodes. So that is one technique that will actually help us solve that case. And then the idea after that is we kind of want to estimate, we'll know the really big nodes because we'll know their exact numbers, and then we kind of want to estimate the remaining nodes. We don't want to cloud our estimate of the remaining nodes with our super big nodes. So essentially what I do is K over 2 times, I pick a random node, I set that, I find the count for that node, and then I pick a random neighbor of that random node, and I set the count for that, and I mark this as one of the special neighbor found nodes. And then at the end, if a node is a neighbor found node, we're just going to add it up. Otherwise, for all the non-neighbor found nodes, we're going to take our best estimate of the average number for them. The way we do that is find all the known nodes that are not in this neighbor found set, which would be things that we found through just teleporting to that room, but we never walked from a neighbor there. Use those as the data we have to estimate the average, and then multiply out that average by the number of non-neighbor found nodes. And so that's my estimate here. Again, divide by 2 at the end just to be safe. Or not just to be safe, but you need to, otherwise you'll be wrong. And went with that. And yeah, so this did better than I expected on this particular judge, which I think is just comparable to what the real judge is, but it got all 100 out of 100. So I don't think it's actually all that good, but maybe it is. Maybe it's better than I thought. Anyway, that's all the problems for today. That's the full problem set. Let's see if anyone else has gotten the 100. Wow, so no one else was able to finish for 100 points within 1 hour. Not even Gennady. Surprising. Oh, okay. Maxime, Endigorian, and Gennady, they're all trying. But Looks like they might need some more time. Anyway, fun little round. Not too bad of a result. Like 2 more minutes or 1 minute faster would have gone second. PWI Peanut was pretty fast. That was a pretty good lead, but you know, I beat Kennedy, so happy about that. Shout out to Kennedy if you're watching. Anyway, thanks for checking out this video. If you liked it, feel free to like the video. It helps out the with the algorithm, and you can check out other videos on my channel as well. But thanks for checking it out, and I'll see you in the next one.